All right, so the next section here, Springs and Hooke's law, is actually a review for us. It comes next in the book, but if you recall, we jumped ahead and we talked about the concept of elastic potential energy, and that was 1/2 k delta x squared. It was also F delta x from work. So the force, though, is what we're going to be taking a closer look at now. And just to review, a force of a spring is negative k delta x. And this formula, reminder that springs always want to be at equilibrium. You can stretch them, you can compress them. They always want to push back to equilibrium. And that's why that negative sign's there. And we'll talk about that, and we'll review that throughout the course of this quick little section. So quick little review. We've assumed that any object that's in equilibrium, like a golf ball, maintains their shapes as forces and torques are applied to them. In reality, and we'll take a look at this in the next section as well, every single object, every solid object can stretch, compress, or deform when a force acts on it. You think about like throwing a water balloon and how the water shifts around and changes the shape of the balloon. Well, that happens with what we would consider rigid objects as well. So there's a little video here of balls getting hit by drivers, and you can actually physically see the compression of the ball. It turns into a little kind of like a D shape, where the ball kind of elongates, and then it actually becomes more of an egg shape before it goes back to being a circle. And these are extreme over-exaggerations of the shape, but that is a golf ball of something that we would normally consider extremely rigid, and the shape that it takes as forces are acting on it. So a quick little review of Springs and Hooke's law. A spring has what's known as a restoring force, and that wants to bring it back to equilibrium. So a spring, I like to always say it's in homeostasis, and it'll do everything it can to stay in homeostasis. Anything that has a restoring force, we call it elastic, and we take a look at how much elasticity it has, and we'll take a look at that, like I said, in the next section when we talk about physical materials and their elasticity. And the spring force is directly proportional to the displacement at the end of the spring. So here I have a spring. It's at its equilibrium length. If it gets compressed or if it gets stretched, some displacement, there is a force that wants to bring that spring back to its equilibrium length. Now, the further and further you push it or pull it, the harder that force is. And if you recall, we did back in energy, work, and power, we did a Hooke's Law lab where we stretched a spring and we measured the force, and we manipulated the force and measured the delta x, or the stretching of the spring, and we did get this nice little linear graph here, where as I increase the force, I'm going to increase the displacement of the spring. So the spring force and the displacement have a linear relationship, and the slope is newtons over meters. So our spring constant has units of newtons per meter, and that is K right there. So here comes our formula then. The force of the spring is K delta X. And of course, like I said earlier, we add that little negative sign, and that little negative sign just means that it's going to oppose whatever direction the force that you are applying is, or the displacement is. So if I pull it to stretch it out, the spring pulls it to compress it back. So that's what that negative sign is just saying, that the restoring force is always opposite the direction of the displacement. So Hooke's Law, it's the most general form of showing how much force a spring exerts based on how far it's stretched. We can also have stuff in the y direction. Now that gets a little bit more confusing, because not only do I have, can I pull something in the y direction, but I can also set this equal to mass times gravity if I have something like a hanging mass, and how much that's going to stretch. So that's kind of what we did in that lab. We will actually take a look at that again in simple harmonic motion. So I got a little quick check here. The restoring force of 3 springs is measured in their stretch, which has the largest spring constant. So as I look at this graph on the left, I think, well, the spring constant is essentially the slope of the line. And a higher spring constant will require more force to stretch it some distance. So A has the largest spring constant. It's the most rigid or stiff spring. So we do have an example that we'll take a look at in class. It's using a spring scale essentially to weigh a fish, and this is an early type of portable scale, and it's still often used in as fishermen, instead of carrying around a digital scale, they'll have a spring scale, so they can literally hook the fish up to the spring scale and determine the weight of the fish, much like we have in our classroom. But anyway, we'll this problem gives us some equilibrium information, gives us the weight of the fish, and how much it stretches. We can solve for the spring constant, and then we can solve for how long the spring stretches or how long the spring becomes if I hang twice the mass. So we'll take a look at that problem in class. And that is your quick little review of springs and Hooke's law, and we're going to take a look at an application of that to close out Chapter 8 in the next section.